In this and the next video, I'm going to be considering first-order linear differential equations. A first-order linear differential equation can be written as dy dx plus some function of x times y equals to some function g of x. Now, the highest derivative is the first derivative because this is a first order differential equation. And we've also got the function itself multiplied by some function of x equals to some function of x. And these functions of x, they could be constants or they could vary depending on x. They could be a whole variety of functions, but they only depend on x, not on y. If g of x is 0, then we have the equation dy dx plus f of x y equal 0, which is the associated homogeneous equation of this equation here. And that can actually be written like this: dy dx equals to negative f of x times y, just subtracting this term here from both sides. And now we have dy dx equals to some function of x, namely negative f of x times y, which is itself a function of y. In this case, it's just y itself, but it's still a function of y. And you'll remember from the previous video that we learned a technique for solving differential equations, first order differential equations, in which they could be written as dy dx equals some function of x times some function of y. So here's our function of x, function of x, and here's our function of y. So this means we already know how to solve this equation and hence this equation, because they're the same equation, it's just this has been rearranged. So we know how to solve this equation, and this equation here is like this equation but with this non-zero or not necessarily zero term or set of terms on the right hand side. So we know how to solve this homogeneous equation, but not necessarily yet how to solve this non-homogeneous equation. Because these are both linear equations, and this is the associated homogeneous equation of this non-homogeneous equation, we can use a technique which will enable us to combine the general solution of this equation with a particular solution for this equation to get the general solution to this equation here, which is this equation here is solving this equation is the goal of this lesson, and also we'll be looking at it in the next lesson as well. Now I'll launch straight into an example of an equation like this, and we'll look at how to solve it. Okay, so an equation of that form would be, one equation of this form would be dy dx minus y equals 5x squared plus 3x plus 2. So this equation here is of this form up here, where f of x is just negative 1, and g of x here is this expression here, 5x squared plus 3x plus 2. Now if we didn't have this expression here, in other words, if we had just had dy dx take y equal 0, we'd have an equation of this form here. Now this equation down here is a different but related equation to this one here. This is the associated homogeneous equation of this equation up here. So it's going to have a different solution, so a different y. So to distinguish the two y's, I'll denote this one with subscript h. So this is yh. Now I've already seen in an earlier video that e to the x solves this equation here. In other words, e to the x has the property that its derivative minus itself equals 0. Because, as you probably already aware, the derivative of e to the x is indeed e to the x. And indeed, any constant multiple times e to the x is also a solution. Okay, so solution to this equation here, yh equals c times e to the x, where c is any constant. So this is a solution to this equation, but if we put it into here, we'll get the derivative minus itself equals 0, not this expression. So we need to add a particular solution that has the derivative minus itself being equal to 5x squared plus 3x plus 2. And then we can add any constant multiple times e to the x to that solution. Because this is a linear equation, the sum of the solution to the homogeneous equation and the particular solution will also be a solution. So I could write that out as y, which is the solution to this equation up here, this is the equation we're interested in trying to solve. The general solution to y is equal to this yh plus some particular solution yp, I'll call it. So we need to find a yp that solves this equation, that gives the derivative minus itself equals 5x squared plus 3x plus 2. So this is one technique for solving non-homogeneous linear first order differential equations. There is another technique that I'll look at in the next video, which involves using what's called an integrating factor. But in this video, what we'll look at is solving first order linear non-homogeneous equations by combining a solution to the associated homogeneous equation with a particular solution to the non-homogeneous equation. Okay, so one way of finding this particular solution yp is what's known as variation of parameter. So yp equals, okay, so what the parameter is that we're going to vary is this parameter here. So this yp is going to be a bit like yh, or we're going to write it out as in the form of yh, except we're going to vary this parameter c. So c is replaced with a function c. What is here a constant c is replaced with a function of x. I call it v of x times e to the power x. So to use this functional form to find a particular solution to this equation here, we substitute this functional form back into this differential equation. And then we find what v is, which requires solving an integral to evaluate what yp is. So yp will just be v of x, whatever v of x turns out to be, times e to the x. Now to substitute that in, we first need to take the derivative of yp, so we can substitute it in here. Now the derivative is just, using the product rule, the derivative of v of x times e to the x plus v of x times the derivative of e to the x, which is itself e to the x. Okay, so substituting that back in, we get dy p dx take yp is going to equal, this is dy p dx, v dash of x plus v of x e to the x minus yp to v of x times e to the x, which according to our differential equation is equal to 5x squared plus 3x plus 2. Okay, now you'll see that this term and this term are identical, so they cancel. This will always happen with this technique, at least as far as I'm aware. Which is useful because now we can solve for this v of x. You can see we've got the v prime of x here, the derivative of v with respect to x, times e to the x equals this term here. So we can just divide by this e to the x, and then we'll just solve for v of x by taking the integral of whatever is left on the right hand side here, which will be as follows: v prime of x equals 5x squared plus 3x plus 2 over e to the x. So we find v of x by taking the integral of this. V of x equals the integral, and I might rewrite this actually as e to the negative x times 5x squared plus 3x plus 2 dx. Through integration by parts, this integral can be solved as follows. So v of x equals this expression here. So that's this expression here is this one here times negative the exponential of e to the negative x minus another integral, and so forth. We take integration by parts a second time as well, and we end up with v of x equals e to the negative x times negative 5x squared take 13x take 15. Now we were looking for yp, a particular solution yp to solve original differential equation, and so finding v of x was just about finding this yp. So now that we've got the v of x, we know what yp is, because yp is just this expression here times e to the x. So it's e to the negative x negative 5x squared take 13x take 15 times e to the x. And of course this and this cancel, leaving us with our particular solution, yp. We can check that this yp is indeed a solution to the original differential equation up here by substituting the derivative of the particular solution and the function that we've derived, and checking that it is indeed equal to this expression here. So first we need to take the derivative of this yp, dy p dx equals negative 10x minus 13, and then we substitute that back into the equation. So dy p dx minus yp will then equal negative 10x minus 13 minus 5x squared minus 13x minus 15, which is equal to 5x squared plus 3x plus 2. Which is as required, 5x squared plus 3x plus 2. So this yp is indeed a particular solution. So the general solution then will just be y equals the general solution to the homogeneous equation, which was this expression here, plus our particular solution. Negative 5x squared, 13x, take 15. And I might rewrite that as c e to the x, take 5x squared, take 13x, take 15. Where c is any constant. Now we can also substitute this whole equation and its derivative back into the differential equation to check that it solves the ODE here, but I won't do that now. In fact, it's probably a good idea for you as an exercise to check that this indeed is a solution to the differential equation. So just to recap what we've done in this example, we had a differential equation here. We have the associated homogeneous equation. We have a solution to that associated homogeneous equation. And then using this technique of variation of parameters, we found a particular solution. And combining the two, c times e to the x, c times e to the x plus the other particular solution, we have the general solution to the equation. Another way to find a particular solution is to look for a function of the appropriate. This is another method we're looking for solving. We're still trying to solve this equation here by combining a particular solution with the general solution to the associated homogeneous equation, but using a different technique to find the particular solution. So another technique to find the particular solution is to look for a function of the appropriate form. Now you can see that the right hand side of this equation is a quadratic. So we'll look for a particular solution that is a quadratic. And then we substitute this particular solution back into our differential equation. So to do that, we have to take the derivative, which I might write as yp dash and then we substitute it back into the equation. So we got dy take y will equal this minus this 2a which is equal to now according to the differential equation it has to equal 5x squared plus 3x plus 2. So this here is equal to 5x squared plus 3x plus 2. So therefore we can read off these coefficients a and we can solve for the b and c. So a here has to equal -5 because negative a has to equal 5 because they're the coefficients of the x squared term. And similarly 2a minus b has to equal 3. 2. And b minus c will have to equal 2. So we already know that a equals -5, so therefore -10 minus b equals 3, or b equals 13. So b equals -13, and therefore if we substitute in that -13 here, we get -13 take c equals 2, so minus c equals 15, and therefore c equals -15. So therefore, our particular solution, yp, which is the form ax squared plus bx plus c, is going to have these a, b, and c. So it'll be -5x squared, take 13x, take 15. Which is the same yp as we got before, using the other technique, the variation of parameter technique. And then if we use this technique down here and got this solution with again, which is exactly the same as the other solution, of course, combining it with the general solution to the associated homogeneous equation would have given us this equation here. So this is another technique for finding particular solutions. Set a trial solution of appropriate form, substitute it in, and then you match the coefficients of the respective terms, so the x squared terms, and in this case an x terms, and the constants. So I'll do one more example of a first order linear differential equation. dy dx minus 1 over x y equals x cubed plus 4x minus 1. So it's a first order equation because the highest derivative is first derivative. It's linear because it only includes linear functions of y and derivatives of y. It's also non-homogeneous because in addition to the terms involving the derivative of y and y itself, it includes these other terms, this function of x, this cubic. So the general form of a first order linear differential equation is dy dx plus some function of x times y equals some other function of x. So in this example here, the g of x here is this function, this cubic, and the f of x is this coefficient of the y term, which is negative 1 over x. Because this g of x function is non-zero, it's non-homogeneous, this differential equation. Okay, so the associated homogeneous equation would be just the same equation with this right-hand side removed. This is the associated homogeneous equation. And it has this, and the homogeneous equation here has a solution y equals ax, where a is some constant. And that, actually, I'll call this YH to know that it's the homogeneous, the solution of the homogeneous equation. This is YH here. To distinguish it from Y, the solution to the equation we're considering, the differential equation we're considering, the non-homogeneous one. And it can easily be shown this is the solution to this equation here. If we take the derivative dyh dx, we get a. So if we substitute a into here and ax into here, we get a dy dx dyh dx, take 1 over x times y, h will equal a minus 1 over x times ax. So that's just equal to the x's cancel, so we're left with a minus a, which is equal to 0. So it solves this homogeneous equation. So to find the solution to the original differential equation, then, as before, we take the sum of the general solution to the associated homogeneous equation with a particular solution to this differential equation, and that will give the general solution to this equation. So in other words, we're looking for a solution to the differential equation of the form y equals yh plus yp, where yp is our particular solution we try to find, and yh is just this ax. So that's equals ax plus yp. So now we have to find this yp. And again, we'll use the method of variation of parameter. So yp, we'll set that equal to some function of x times x. Again, we're varying this parameter here, this constant a, to find some particular solution yp of the form some function of x times x. So, and we do that by substituting this form back into the original differential equation. So if yp equals v of x, then dy p dx will equal v prime of x. That's the derivative of v with respect to x times x plus v of x times, well, the derivative of x with respect to itself is just 1. So that's the derivative of yp with respect to x using the product rule. Okay, so substituting back into the differential equation will give v prime of x times x plus v of x, take 1 over x, times yp, which is v of x times x. And now these x's cancel, which means that we have v of x minus v of x. So the v of x is also cancel. And that's as before. We'll always get that the v of x times the derivative of this function will cancel with the term we get when we from this term. So that, according to our differential equation, is equal to x cubed plus 4x minus 1. Okay, so now we can solve for this v of x, and in doing so, then we'll be able to find what yp is equal to. So therefore, v dash of x is equal to x cubed plus 4x minus 1 over, divide through by x. So that means that v of x is equal to the integral with respect to x. Now we'll just separate these out into separate fractions. So we'll get x squared plus 4 minus 1 over x now the integral of the sums is just going to be equal to the sum of the integral, so we just take the integral of each term, or an antiderivative of each term. So we'd get x cubed over 3 plus 4x minus natural log of x. Now, there's usually an integrating constant. So if we're taking the integral of all of these terms, then we get a constant for each of them. Or if we're taking, but a constant plus another constant will also equal a constant itself. So we could just have an extra constant, or just one constant for this whole expression. We actually don't even need that extra constant because we're finding this v, so we can find yp, and if we added some constant here, like c, then when we multiply this v of x by x, So we multiply this v of x by x to get yp. We'll get some extra cx term, but we don't need that extra cx term because having a constant times x is just the same as the ax, which is in our solution already. So in other words, rather than having ax, we'd end up with having a plus c times x. But a plus c times x, some constants a and c, is still just some constant times x. So we might as well just stick with ax. Actually, I'll keep the c just to show you what I mean. So that means that therefore yp equals to this whole expression times x, according to what we define yp to be equal to. That will be equal to x to the power 4 over 3 plus 4x squared minus x log x plus cx. So that means that our general solution to the differential equation, yh plus yp or ax plus yp, is equal to ax plus x to the 4 over 3 plus 4x squared, take x times log of x plus cx. And you can see we've got some constant times x and some constant times x, and we don't need both of them. I mean, they could be, we can factorize that to have y equals a plus c times x plus x4 y by 3 plus 4x squared, take x log the x. But we might as well just have y equals ax plus x 4 over 3 plus 4x squared minus x log x, where a is some unknown constant, so we don't need, so a is an element of R, a is some real number. We don't need to have, so we don't really need to keep this cx, we could have just, and therefore we don't need to have that c in the v of x, because adding this integrating constant will just give us another, give us a function that's equivalent to the general solution to the homogeneous equation, which is already in our solution that we've defined, y equals ax plus p. So that constant times x function within the solution is already included, so we don't need to add this cx or this c, and therefore we don't need to add this c in the v of x. Okay, so this is the solution that we've found. And we can check that it indeed solves the differential equation. So we just need to substitute this into here and take the derivative and substitute that in there, and we'll check that it equals x cubed plus 4x, take 1. So to do that, we'll take the derivative of this term here. So this implies that the derivative equals a plus 4/3 x cubed. We have our derivative here. A plus 4/3 x cubed plus 8x. Take x over x, which just take 1 minus log of the absolute value of x. So substituting the derivative and the function itself into this expression here, we get a plus 4/3 x cubed plus 8x minus 1 minus log of x minus 1 over x times ax plus x to the power 4 over 3 plus 4x squared minus x log x, which is equal to, okay, so these x's cancel out, so we left with a minus a, which is good, the 8 goes away, and then we have 4/3 x cubed minus x cubed over 3, that's just x cubed, plus 8x minus 4x, this is going to be 4 minus plus 4x, and then we have minus 1 and the negative log of the absolute value of x, and so minus times a minus is a plus, so that's plus x log of absolute value of x divided by x, which is just plus log the absolute value of x. So that's those two terms cancel out as well. So we're left with x cubed plus 4x minus 1, which is in accordance with the differential equation. So this function here does satisfy that differential equation. So in solving this differential equation here, we've now solved two first-order linear differential equations. In the following lesson, I'll look at another technique for solving first-order linear differential equations. It will use what's known as an integrating factor.